In the winter of 2001, inside a laboratory at Harvard University, a physicist named Lene did something that sounds like it belongs in fiction. She took a beam of light, the fastest thing in the known universe, the thing Einstein built the entire architecture of modern physics around, and she stopped it. Not slowed it down, not delayed it, stopped it. Frozen, motionless, sitting inside a cloud of ultra-cold atoms, like a photograph trapped in glass. For a fraction of a second, in that lab, the rulebook of the universe seemed to bend. This case file is not about a magic trick. It is about a real, peer-reviewed, repeatable experiment that forced physicists to rewrite what they thought they understood about light, matter, and information. And by the end of this investigation, we are going to follow that discovery somewhere you would not expect, into one of the most unsettling questions in all of science. Not how did they stop light, but why, if the universe is so vast and so old, have we never heard from anyone else in it? Because as strange as it sounds, the physics of frozen light and the silence of the cosmos are connected by the same underlying principle. And once you see the connection, you will not be able to unsee it. Let's start with the credibility stamp, because a claim this strange demands one. The experiment we are discussing was conducted by Dr. Lene, a Danish physicist, along with her research team at the Roland Institute for Science and Harvard University. Their work was published in the journal Nature, one of the most rigorously peer-reviewed scientific publications on Earth. The first landmark paper, released in 1999, demonstrated that light could be slowed to 17 meters per second, slower than a bicycle, by passing it through a Bose-Einstein condensate, an exotic state of matter that only exists at temperatures a fraction of a degree above absolute zero. 2 years later, in 2001, Howe's team went further. They didn't just slow the light down, they brought it to a complete stop, stored the information it carried inside the atomic medium, and then released it back into motion, reconstructing the original light pulse almost perfectly. This second result was also published in Nature, and it has since been replicated and expanded upon by multiple independent research groups, including teams at the Massachusetts Institute of Technology and in laboratories across Europe. This is not fringe science. This is some of the most carefully verified experimental physics of the last 3 decades. So how do you even begin to stop something that, by definition, cannot stand still? Light is not like a car or a river. It doesn't coast to a halt through friction. In a vacuum, light always travels at exactly one figure, 299,792,458 meters per second. That number, c, is not a suggestion. It is stitched into the geometry of the universe itself. And yet Howe's team found a loophole, not in the vacuum, but in matter. Here is the reversal, the moment where the story stops being simple. Light doesn't actually slow down when it passes through glass, water, or a diamond. What happens is far stranger. The photons, the individual particles of light, are absorbed by the atoms of the material and then re-emitted over and over in a relay race that takes time to complete. The photon itself never travels slower than light speed. It's the constant absorption and re-emission by the surrounding atoms that makes the light appear to slow down as it crosses the material. This effect is why a laser pointer beam bends when it enters water, an effect called refraction, first rigorously described mathematically by the Dutch physicist Willebroord Snellius in the early 17th century, and later folded into Isaac Newton's studies of optics. Under normal conditions, this absorb and re-emit relay happens so fast that light through glass still travels at over 200 million meters per second. But Lene Howe's team engineered a very different kind of material, a Bose-Einstein condensate, first predicted theoretically by Albert Einstein and the Indian physicist Sachendra Nath Bose in the 1920s, and not actually created in a laboratory until 1995 by physicists Eric Cornell and Carl Wyman at the University of Colorado Boulder, an achievement that later earned them the Nobel Prize in Physics. A Bose-Einstein condensate is created by cooling a cloud of atoms, in Howe's case sodium atoms, to within a few billionths of a degree of absolute zero. At that temperature, the individual atoms lose their separate identities and begin behaving as a single collective quantum entity. It is one of the strangest and most fragile states of matter known to science. Inside this condensate, Howe's team used a technique called electromagnetically induced transparency. In simple terms, they used a second control laser to manipulate the quantum states of the atoms in the condensate, essentially opening and closing an optical window. When the window was open, the light pulse would enter the condensate and interact so strongly with the ultra-cold atoms that its effective speed dropped to a walking pace, 17 meters per second in the 1999 experiment. When the researchers then shut the control laser off entirely, something remarkable happened. The light pulse didn't just slow down further, it stopped. Its energy and quantum information were transferred completely into the collective spin state of the atoms in the condensate. The photons, in a sense, stopped existing as light and became an imprint, a pattern etched into matter itself. This is the reversal that changes how we think about information. The light wasn't destroyed, it was translated. Its entire pattern, its phase, its shape, its quantum information, was stored in the atomic medium like a song encoded onto a vinyl record. And when Howe's team turned the control laser back on, the atomic condensate released that stored information, and a pulse of light re-emerged, reconstructing the original signal with high fidelity. They had, in effect, built a light hard drive, a memory device made of matter, storing something as ephemeral as a beam of light, holding it and then playing it back. To appreciate how fragile and precise this process really is, it helps to understand just how extreme the conditions inside Howe's laboratory apparatus actually were. A Bose-Einstein condensate does not tolerate disturbance. The sodium atoms used in Howe's experiments were first slowed and trapped using laser cooling techniques, a method pioneered by physicists Stephen Chu, Claude Cohen-Tanucci, and William Phillips, work that earned them the Nobel Prize in Physics in 1997. Laser cooling uses carefully tuned beams of light to repeatedly nudge atoms in the opposite direction of their motion, gradually stripping away their kinetic energy until they slow to a near standstill. From there, the atoms are confined using magnetic traps and cooled further through a technique called evaporative cooling, essentially allowing the highest energy atoms to escape the trap so that only the coldest, slowest atoms remain. The same basic principle behind how a cup of coffee cools faster when you blow across the top of it. The result, after this multi-stage process, is a cloud of roughly a few million atoms cooled to temperatures measured in billionths of a degree above absolute zero. Colder than anywhere else in the known universe, including the depths of interstellar space, which typically hovers a few degrees above absolute zero due to residual heat left over from the Big Bang. At these temperatures, the sodium atoms stop behaving like a normal gas made of distinct, independently moving particles. Instead, governed by the quantum statistics first worked out by Bose and Einstein in the 1920s, the atoms collapse into a single shared quantum state, essentially losing their individual identities and behaving as one unified quantum object, sometimes described as a superatom. It is only within this bizarre, ultra-cold, quantum-mechanically unified medium that light can be made to interact so strongly and so precisely that its motion can be controlled down to a dead stop. Try the same experiment with light passing through ordinary glass or air, and the interaction is far too weak and far too disordered for anything like this to occur. It is precisely the exotic, fragile, laboratory-engineered nature of the Bose-Einstein condensate that makes Howe's result possible at all, which is part of why it took until 1999, over 70 years after the condensate was first theoretically predicted, for anyone to actually observe one, let alone use one to manipulate light. This alone would be one of the most significant results in quantum optics of the last half-century. Researchers have since used variations of this technique to explore quantum memory devices, which are considered essential building blocks for future quantum computers and quantum communication networks. Because storing and retrieving quantum information without destroying it is one of the central bottlenecks in building a functional quantum internet. Work from research groups including those at the California Institute of Technology and the Australian National University has continued to push this frontier, storing light for longer durations and in more stable media, including doped crystals cooled to cryogenic temperatures. But here is where this case file takes its turn, the moment we bring in the reality check, our recurring investigation into what a discovery actually proves once you strip away the sensational headlines and look only at the evidence. Because there's a temptation when you hear scientists stopped light to imagine warp drives, time travel, or violations of relativity. None of that happened. Einstein's speed limit remains completely intact. The photons in Howe's experiment never exceeded, met, or broke the vacuum speed of light. They were absorbed and converted into atomic information, then reconstructed later. It's less like light broke the rules and more like light checked itself into a very strange hotel, left its luggage in the safe, and walked back out later wearing the same clothes. The physics is not about breaking the speed of light. It's about revealing just how deeply light and matter are entangled, how conditional our everyday assumptions about physical constants really are, and how information itself, not just particles, is the real currency of physics. And this is precisely the thread that pulls us toward the second half of this case file, the part where frozen light in a Massachusetts lab starts to explain something about the deafening silence coming from the rest of the universe. To understand why, we need to revisit a question first posed with startling simplicity by the physicist Enrico Fermi in 1950, during a lunchtime conversation with fellow scientists at Los Alamos National Laboratory. The story, as retold by physicist Eric Jones in a 1985 Los Alamos technical report documenting the recollections of those present, describes Fermi doing some rough mental arithmetic about the sheer number of stars, the likely fraction with planets, the probability of life arising, and the timescales involved for a civilization to spread across a galaxy. And after doing this math in his head, Fermi reportedly asked a single, deceptively casual question: "Where is everybody?" This became known as the Fermi paradox, and it has haunted astronomers, physicists, and search for extraterrestrial intelligence researchers for over 70 years. The scale of the numbers alone makes the silence deeply strange. The observable universe contains an estimated 2 trillion galaxies, according to research published in the Astrophysical Journal by astronomer Christopher Gonzalez and colleagues in 2016. Our own Milky Way galaxy alone contains between 100 billion and 400 billion stars, and data from NASA's Kepler Space Telescope mission, launched in 2009, has allowed astronomers to estimate that our galaxy likely contains billions of potentially habitable, Earth-sized planets orbiting within the habitable zones of their stars. Even if only a vanishingly small fraction of those planets ever develop life, and an even smaller fraction of that life ever develop technology capable of communication, simple statistics suggest we should not be alone. And yet, despite decades of dedicated listening by projects including the SETI Institute's radio telescope surveys and NASA's own now-defunct high-resolution microwave survey, we have detected exactly 0 confirmed signals from another civilization. This silence is the mystery, and for decades the explanations offered have ranged from the mundane to the genuinely unsettling. Some, like the Great Filter hypothesis, first formally articulated by economist and researcher Robin Hanson in a 1998 paper, suggest that there is some improbable step in the development of life or civilization that almost nothing manages to pass through, meaning either we are freakishly rare survivors of an evolutionary bottleneck, or every civilization eventually destroys itself before it can reach the stars, a deeply sobering possibility given humanity's own 20th century brush with nuclear annihilation. Others, like the dark forest hypothesis, popularized in science fiction but rooted in real game-theoretic reasoning, suggest that civilizations deliberately stay silent out of self-preservation because broadcasting your location to the universe might be like shouting into a dark forest full of unknown predators. But there is a quieter, more physically grounded explanation gaining traction among astrophysicists in the past decade, one that connects directly back to what Lene discovered in her lab. And it has to do with the assumption baked into nearly every SETI search since the project began in 1960, with astronomer Frank Drake's project OSMA. The assumption that an advanced civilization would communicate the way we do, with electromagnetic radiation, with radio waves and light, broadcast outward, hoping something, somewhere, is listening on the right frequency at the right time. This is where the rewind of this case file happens, because Howe's stop-light experiment demonstrates something profound about the relationship between light and information that most people, and even most early SETI researchers, never fully accounted for. Light, as a carrier of information, is extraordinarily fragile and extraordinarily wasteful across interstellar distances. When Howe's team stopped a pulse of light, they proved that light's information could be transferred completely into a stable, static medium, atomic spin states in a condensate, and that this stored information behaves completely differently from freely traveling light. It doesn't disperse, it doesn't weaken over distance the way a radio signal does, spreading its energy across an ever-expanding sphere until it becomes indistinguishable from background noise. Once light's information becomes matter-encoded, it becomes durable, local, and stable, rather than transient and radiative. Now scale that principle up to the level of galactic civilizations. A radio or optical signal broadcast from a star system doesn't stay strong. Its intensity falls off according to the inverse square law, first rigorously formalized by Newton, meaning that by the time a signal from even a relatively close star, say 100 light-years away, has traveled that distance, its strength has been diluted across an area so vast that detecting it requires equipment sensitive to an almost unimaginable degree. And even then, only if the signal happens to be aimed with pinpoint precision at Earth, at the exact time we happen happen to be listening, on the exact frequency we happen to be scanning. Our own SETI search efforts, even the Modern Breakthrough Listen initiative, launched in 2015 with funding from the Breakthrough Foundation, can only realistically scan a minuscule fraction of the sky, over a minuscule slice of the electromagnetic spectrum, for a minuscule sliver of time, compared to the scale of the galaxy and the age of the universe. Astronomer Jill Tarter, a former director of the SETI Institute, has publicly compared our search efforts to sampling a single glass of water from the entire Earth's oceans and concluding there are no fish. This is the escalation. It is entirely possible, and increasingly considered plausible by researchers in the field, that the silence we perceive is not evidence of absence, but evidence of a mismatch in method. If advanced civilizations, after developing technologies analogous to what Howe demonstrated, or far more advanced descendants of it, learned that broadcasting information as radiative energy across the vacuum of space is staggeringly inefficient compared to encoding and transmitting information in more stable, directed, or matter-based forms, they may have simply stopped using the kind of communication we are built to detect. Physicist and SETI researcher Paul Davies, in his 2010 book The Eerie Silence, directly raised this possibility, arguing that our search strategy is built on the unstated assumption that advanced intelligences would still be using 20th century human communication technology, when in reality any civilization even a few centuries more advanced than ours might have moved to information transmission methods we haven't even conceived of yet, let alone built the instruments to detect. Howe's frozen light experiment is a small, laboratory-scale proof that information does not have to travel as loose, dispersing electromagnetic radiation. It can be captured, held, and moved as something closer to matter, dense, directed, stable, and vastly more efficient. If a civilization existed that had mastered something like this on a planetary or even stellar scale, their communication might not look like a radio signal spreading outward and weakening. It might look like nothing we currently have the instruments to notice at all. It's worth pausing on just how strange this makes the entire premise of a SETI-style search. When Frank Drake pointed the Tatel radio telescope at the stars Tau Ceti and Epsilon Eridani in 1960 during Project Ozma, he was making a very specific bet that an alien civilization, if it wanted to be found, would use electromagnetic radiation in a frequency range convenient for us to detect, would broadcast with enough power to survive the inverse square law over light years of empty space, and would do so continuously or repeatedly enough that a brief listening window on Earth might catch it. Every subsequent SETI search, from the Arecibo Observatory's decades of sky surveys to the modern Allen telescope array built with funding from Microsoft co-founder Paul Allen, has operated on some version of that same bet. It is a reasonable starting assumption because radio was the most advanced information transmission technology humanity had when the search began. But reasonable starting assumptions are exactly the kind of thing that rigorous, evidence-based inquiry is supposed to keep testing, not keep accepting by default. And Lene Howe's laboratory result is one of the clearest experimental nudges physics has given us that the assumption deserves testing. Consider the numbers again, because the scale here matters more than the abstraction. A typical radio broadcast loses intensity proportional to the square of the distance it travels. A signal that could be picked up clearly from 10 light years away would need to be transmitted with roughly 4 times the power to remain detectable at 20 light years, 16 times the power at 40 light years, and so on, compounding brutally as distance increases. To broadcast a signal detectable across even a modest slice of our own galaxy, tens of thousands of light years in diameter, would require energy expenditures on a scale that starts to strain the output of an entire star, a concept physicist Freeman Dyson explored theoretically in his 1960 paper on what became known as Dyson spheres, hypothetical megastructures built to capture a star's total energy output. Radiative broadcasting across galactic distances is not just inefficient. For anything short of an almost inconceivably advanced civilization, it may simply be impractical. This connects to a related and equally important piece of evidence: the sheer difficulty of transmitting a signal fast enough to be practical across interstellar distances in the first place. Even a message traveling at the speed of light takes over 4 years to reach our nearest stellar neighbor, Proxima Centauri, and over 100,000 years to cross the diameter of our own galaxy. A back-and-forth conversation between two civilizations light years apart isn't really a conversation in any meaningful sense. It's closer to two people writing letters they know won't be answered for millennia. Physicist Michio Kaku has pointed out in multiple public lectures and writings that any civilization advanced enough to survive long term would almost certainly need to solve this information transmission efficiency problem, precisely the kind of problem Lene Hau's laboratory was, in miniature, beginning to solve. The bridge to now is this. The very techniques being developed today in quantum memory research, building directly on Hau's foundational work, are aimed at exactly this challenge. How to store, stabilize, and transmit information without the massive losses inherent to radiative broadcasting. Quantum communication satellites, including China's MESIUS satellite launched in 2016, have already demonstrated entanglement-based communication across over 1,000 kilometers, a technology fundamentally different in character from a traditional radio broadcast, and one that does not radiate outward in the same detectable, ever-weakening way. None of this proves that alien civilizations exist and are deliberately using undetectable communication methods. That would be overstating the evidence, and this channel does not deal in unresolved sensationalism. What the evidence does support, carefully and conservatively, is this. Our failure to detect extraterrestrial signals cannot be treated as strong evidence that no one is out there, because our search has been built almost entirely around the assumption that intelligent life communicates the way 20th century humans do, through radiative electromagnetic broadcasting. Lene Hau's stoplight experiment is important here not because it is about aliens at all, but because it is hard experimental proof that light and the information it carries can be manipulated, stored, and transferred in ways dramatically different from simple radiative transmission. It demonstrates in a controlled laboratory setting that the assumption baked into SETI's search strategy that advanced information transfer must look like a signal spreading outward through space is not a law of physics. It is a limitation of our current technology and imagination. The human cost of this insight is subtle, but it is real. For over 60 years, some of the most brilliant minds in astronomy have poured their careers into listening for a whisper across the stars, funded by philanthropic donors, public grants, and sheer scientific persistence, often facing public skepticism and, at times, ridicule for taking the search seriously at all. Frank Drake, who died in 2022, spent his entire life advocating for the legitimacy of this search, formulating the famous Drake equation in 1961 to estimate the number of detectable civilizations in our galaxy, a formula that remains foundational to the field despite the enormous uncertainty in many of its variables. Jill Tarter dedicated decades to refining our listening strategies. And what discoveries like Hau's remind us is that the silence these researchers have encountered may not be a verdict on whether we are alone. It may simply be a verdict on how narrow our current listening posture is. This reframes the entire question posed at the start of this case file. We didn't stop light in a lab and stumble onto proof of alien silence by magic or coincidence. We stopped light in a lab and, in doing so, revealed a fundamental truth about how information and radiation relate to each other. A truth that directly undercuts one of the quiet assumptions baked into humanity's entire search for cosmic company. It suggests that the next real breakthrough in the search for extraterrestrial intelligence may not come from bigger radio telescopes scanning more of the sky. It may come from rethinking what a message from another world would actually look like in the first place, guided by exactly the kind of quantum information physics Lene Hau's team pioneered over 2 decades ago. Today, research building on Hau's original stoplight work continues at institutions around the world. Physicist Mikhail Lukin at Harvard has extended this research into networks of quantum repeaters, devices designed to preserve and relay quantum information across long distances without the signal degradation that plagues classical broadcasting, a technology explicitly aimed at solving the exact long-distance information transfer problem that may be relevant to how a truly advanced civilization would choose to communicate, whether across a laboratory bench or across a galaxy. Meanwhile, the search for extraterrestrial intelligence itself has begun to diversify. The Breakthrough Listen initiative has expanded its search parameters to include optical laser pulses, not just radio frequencies, precisely because researchers have started acknowledging that a genuinely advanced civilization might not be using the same communication toolkit we defaulted to in the 1960s. Astronomer Avi Loeb, former chair of Harvard's astronomy department, has gone further still, arguing publicly that the search for extraterrestrial technology, sometimes called the search for technosignatures, needs to expand beyond radio and light entirely to include the possibility of physical artifacts, unusual material signatures, and entirely novel information carriers we have not yet learned to recognize. What Lene Howe's frozen light ultimately teaches us is a lesson in humility about the limits of our own assumptions. For most of human history, we assumed light was the fastest and most fundamental thing in the universe, immutable and untouchable. Then a physicist in a Massachusetts laboratory demonstrated that under the right conditions, light's information could be captured, held still, and released again, revealing that even something as fundamental as the speed of light in a medium is a negotiation between energy and matter, not an absolute rule written in stone. If our assumptions about something as well understood as light could be this incomplete, it stands to reason that our assumptions about how an alien civilization would choose to communicate across the vastness of space are at best provisional and at worst badly outdated. This is the real answer to the question posed by this video's title, and it is not the answer of science fiction. It is not confirmation that extraterrestrial life exists, and it is not proof of some hidden alien silence pact. It is something more interesting and more scientifically honest than either of those. It is evidence that our search for cosmic company has, for over half a century, been built on a communication assumption that a real laboratory experiment has since shown to be fundamentally limited. The silence from the stars may not be silence at all. It may simply be a frequency, a format, and a physical medium we have not yet learned to listen for. And the very same physics that led a team of researchers in Cambridge, Massachusetts, freeze a beam of light into stillness inside a cloud of sodium atoms may, one day, be the key that finally lets us hear whatever it is that has been out there all along. For now, the case remains open. The evidence tells us that our silence-based conclusion of cosmic solitude does not hold up under scrutiny, because the method behind that conclusion is built on an assumption about communication that laboratory physics has already begun to dismantle. Frank Drake's equation still stands as a framework. Jill Tarter's decades of listening still matter. Paul Davies's warning about our narrow search strategy still echoes through the field. And Lene Howe's frozen light, sitting quietly in the history of quantum optics, remains one of the most underappreciated pieces of evidence, suggesting that the universe may be far louder than we think. We simply haven't built the right kind of ears yet. That's the file for today. If this investigation into frozen light and cosmic silence expanded how you think about the universe's greatest unanswered question, stay subscribed, because this channel exists to keep opening cases like this one, grounded in verifiable evidence, resistant to easy sensationalism, and committed to following the facts wherever they actually lead. The next file is already open.